we've been doing tree assessment as wood decay detection for conservation jobs together with Prof. Yo for the last few years. I can't remember when we started. But because the science is transferable, and then it was getting a bit boring on the arboriculture side. So we decided, yeah, why not, try this. And then it was interesting. I mean, so far the journey has been quite interesting for us. Okay, for wood detection, for wood decay detection, right, there are 2 levels of assessment. Okay, when we head in, right, we will do a visual assessment first. Okay, I'll run through what are the visual indicators. If there are indicators to suggest there is decay in the wood, right, it goes to the 2nd level, equipment detection. Okay, there are 2 types of equipment that I'll be going through. One is the resistograph, and the other one is the more, in the industry term, more sexy pikers. Actually, arboriculture wood defect detection, right, actually started from lampposts, from the need to detect decay in lampposts. In Singapore, we don't have wooden lampposts, but overseas they have a lot. And the primitive way, right, was to use hammer. They'll just knock, and then it's more art than science. I mean, in every profession, there's the science and there's the art of things. For the last 10 years, right, arboriculture work, the science in arboriculture work has been moving forward quite rapidly, and then we have gathered quite a lot of science to wood detection, wood decay detection. So gone are the days where the inspector uses a wood and then he sound off the candidate and decide, whether there's a decay or not. Nowadays, with instrumentation, right, you can actually quantify, not only detect the presence, but actually quantify the presence, quantify the amount of decay. Okay, the diagram you see here is a resistograph. I'll go through in detail how that works when it's applied to conservation works. Okay, visual tree assessment. This is actually, if I were to go through visual tree assessment, it will be a 2 to 3 day course, but I'll just truncate it really to the basic level for you guys in about 5 minutes. Okay, when I was in year 2000, when I was first hired by the National Parks Board, they hired me before I graduated. So, and they were pushing for arboriculture work. But in that year that I was hired, right, there were only, when they sent me out to the field, there were only a few things I was looking out for: open cavity, termite tracks, cracks, and that's it. There wasn't any real science to it. Okay, nobody taught me what kind of decay, what kind of structure we are looking at, whether a crack is dangerous or can be mitigated. So if you look at these 2 pictures, right, even in a layman's context, there'll be a certain level of discomfort, right? Tree with such a large decay would have structural issues. Similarly, a tree with exposed wood like this, and then you can see that there probably was a cavity here, and then they fill up with cement. So the question is, how stable is this tree? Okay. So similarly, in conservation projects, right, you will have columns of wood. Okay. If you see the condition of the wood beyond the norm, you would suspect there's some defects or some impairment to the structural integrity. For tree assessments, right, because of the biology of the tree, right, you notice when we see a fallen tree, right, it's full of foliage, and then you're saying, hey, the tree is so healthy, why did it fail? It's because the biology of the tree, the live tissue is only in the outer layers. So we differentiate tree assessment into two levels, two different things: the tree health and its structural stability. Okay, these two are actually assessed differently. Okay, the tree can be very healthy, but because it has a big decay, right, it is not stable. Okay, but for conservation, right, for conservation work, right, we're strictly only dealing with the dead stuff. We're not looking at the live section of things. Okay. Okay, the other thing about visual tree assessment, if you see a bracket fungus, right, at the base of the tree, or anywhere on the tree, right, it's an indication there's internal decay. Okay, this is obvious, right? I mean, it's outwardly obvious, but this tells you that there's a decay inside which is not outwardly obvious. For us, right, for tree inspectors, right, every time we see fungal fruiting bodies, right, automatically it leads to a second level instrument assessment. Okay, if you don't do instrument assessment and there's decay and there's a fruiting body and the tree fails, right, the attending arborist is liable. Okay. Okay, this is one type of fungus where, you know, the fungus has shown you, expressed itself as a fruiting body, a mushroom, literally. But there are other fungus, right, that don't express themselves as fungal fruiting bodies. So this is a edge of a door, okay, and you see that it has sort of like blistered out, and then if you went and you took a piece of it, it's soft, okay, and it's very brittle. It feels like biscuit. Okay, this is what is known as a white rot. Okay, in terms of mechanism, right, the fungus degrades the cellulose and the lignin of the material, or the wood material, then break up all the structure, and this results in this kind of papery feel. Okay, so this is with fruiting bodies. This is fungal attack with fruiting bodies. This is fungal attack without fruiting body. Okay, this is a cavity on a branch. You may see that we saw a very large cavity on the main trunk, but in a lot of our trees, right, there are cavities on prune sections of branches. Okay, it may look small from the outside, but if you do an instrument detection, you may find that the cavity may have gone all the way down. Okay. Cracks. Okay, there's to us, at any point of time we see cracks, right, either on the branch or the trunk, right, we consider it, we will have to do something about it. If it's on the trunk, most likely we have to remove the tree, because the crack, right, is hard to mitigate. If you leave the crack will continue to propagate and in fact eventually lead to failure. Okay, these are splits. This is a result of two very heavy bifurcations. Okay, and in the next slide, I'll tell you how to decide when this kind of split will happen. Also, if you notice, right, certain trees, right, when there's an exposed section, right, and then you start to have adventitious roots coming out, this is an indication that the lower section of the roots, right, are no longer functioning, and the tree adapts to it, right, by trying to put out new roots to compensate for the roots that they lost. Okay, and because roots are the anchoring structure of the tree, right, if you see that half the tree, right, is putting out adventitious roots, right, although the tree is healthy and in good vigor, right, it may no longer be that stable because the roots are no longer functioning. Okay, this is what we call exposed deadwood. Do you think it's a defect? It's a defect that warrants attention? Do you think it does? Remember I told you that the only live section of the wood, right, is on the outer layer. 90% of wood that is made out of dead material. And the tree derives stability from this dead material. So dead material is not actually a bad thing. Okay, it's whether the dead material is degrading that you have to decide and measure and then come up with an assessment whether the degradation has impaired the stability enough. Okay, so in this kind of in this context, right, this is very similar to the conservation projects that we do. Okay, first, the visual assessment of the wood, right, is that there is no abnormal discoloration. Okay, if I were to cut this tree and then I were to saw into planks and then I were to weather it in the open, right, this will probably be the color that it comes to in about a year. So no discoloration. So the other thing we're looking out for is fruiting bodies. If there's no fruiting bodies here, that means the wood is not being degraded by fungal activity. Okay. The third thing we're looking out for is whether there are borer activities. These little holes, right, you'll see. Sometimes in your cabinet, right, you see these little holes that go in, right? And then if it's fresh, right, you see this powder stuff that accumulates at the bottom. There's no borer activity here. Okay. Fourth, no termite activity also. If you see termite tracks, there are about 9 common termite species in Singapore. Only 2 of them are aggressively wood degrading. Okay, the rest are what we call bark feeders. All of them are in some way important for ecology. It's whether the guy is degrading the wood that you want to retain. Okay. So 4 things. These are the four things that we look out for when we're on conservation projects also. Okay, abnormal discoloration, fungal fruiting bodies, borer activities, and termite activity. So in this picture, right, you don't see any of them. So it's just purely exposed dead wood. Okay. You see this section coming in here. That's a bit messy. Okay. This is what we call wound wood roll. It's a tongue twister, but it's a tree's reaction to exposed wood. So eventually, right, this thing will start to multiply and it will grow, and the exposed wood will grow. Exposed area will shrink. So given a few years, right, this whole section may be covered up. Okay. Okay. In conservation context, this is usually what you see. Uniform bowl with no flare. But in empirical arboriculture work, we really don't like this. Okay, we prefer trees with flares, root flares. Root flares means stability. Okay, if you look at lampposts, right, and if you look at the base of lampposts, right, you see that some of the structural engineers, they put wings on it, triangular wings. So it's similar to root flares on trees. It stabilizes the tree, or it enhances the stability of the tree. Okay, we talked about unions. So you remember the split I showed you just now? How the bifurcation split? If it's a V bifurcation, V crotch, it's less stable than a U union. A U union to us is a very stable, safe and stable bifurcation. Okay, this U union will be able to take more load than a V. In the next slide, I'll show you why. Oh, you notice this little crack here? Okay. So V bifurcation has, if you section it right, you'll find that there is an internal crack within a very sharp V bifurcation. This is known as included bark. So what happens is that if both of these branches continue to grow, they'll continue to push their bark into this crack, and eventually they'll split. Okay? Okay, so this part, we've come to the end of the visual assessment. So if at any point I see there's discoloration, there's borer activities, there's fungal fruiting bodies, right, I'll go into equipment assessment of the wood. Okay. this is the equipment that we're using now. It's the IML 400 PD. 400 means is the length of the detection is up to 400 mm. This is 40 centimeters, which is sufficient for most of the trees in Singapore and more than sufficient for conservation projects. Okay, how does this work? So the advantage of the resistograph, first, it has the ability to confirm the decay for you, the internal decay. Remember the picture of the fungal fruiting body? We know there's a decay inside, but we want to confirm it. So with that machine, the resistograph, we can confirm the decay, okay? And with that machine also, we can evaluate the size of the decay. I think I've got a slide to tell you what's the failure criteria for trees. How much decay before we fail the tree. Then you can also determine whether this decay is propagating or not. Okay, if you have just a small decay and the decay is not propagating, then you're fine. Okay, but if you have a small decay and that decay is propagating, then you may have to do a prognosis on how long more can you retain that piece of wood or the tree before decay becomes significant to impair the wood structure to predictable failure. Okay, because it's a micro drill, right, we'll show you the size of the drill later. It doesn't result in large holes and it's not considered invasive. It's just a dot. At the end of the drill, it's just a dot. It's much faster in application than the Picus ultrasound, which I'll go through later. Okay, it's easily portable. It's easy to use and portable at height. A lot of the conservation work, right, a lot of tree works involves us going on a crane, going to the branches to drill the tree. Okay, and similarly for conservation projects, right, we have to go up to the columns and the beams to drill. So if it's heavy and not portable at height, right, it's not a good equipment. Okay, but this is small and light enough to be portable. Okay, like all things, right, there's a limitation to it. The primary limitation to any equipment is the operator. Okay, it's one of those rubbish in, rubbish out. If you're not well trained or you don't know what you're looking at, then you can't determine you can't assess the quality of wood adequately. Okay, resistograph uses relative resistance. So because it's relative resistance, right, you always have to get a reference drill, okay, from the section where you think there's no decay or no defects. And from this reference drills, right, all other drills are referenced to it. It's the size of the needle. Okay, it's only 3 mm and it's formed like a spade. What it does when it enters the wood, right, is that it actually pushes the wood aside. It doesn't drill or remove the wood, it just pushes the wood material aside. And when it is extracting out, right, it will pull back this wood material and clog the hole that it has created. Okay. And at 3 mm, right, that's minuscule. It's really, really small. IML from the manufacturer, one needle can do 100 to 150 drills. Okay, but this equipment was designed and made in temperate countries. And do we have harder wood in the tropics? We have much harder wood in the tropics. Okay, this equipment was made by a German professor called Klaus Martek. Many years ago, when he came to Singapore, right, he brought his equipment and then to teach us how to use it on trees. And we were quite mischievous. We brought him to the hardest tree wood we had which is actually, do you know the hardest wood we have locally? One of the hardest wood? Close. Temusu, there's another one. You know there's a correlation between fast growing and wood quality, right? Yeah, but there are few of them who flout this rule. They are fast growing and very high in density. Do you all know them? Okay, Tembusu is slow growing and very hard, so it's in line. But acacia and casuarina wood is very fast growing, but they have very high wood densities. After last few slides, I will show you wood density level. But anyway, we brought him to a casuarina tree. So when he started to drill, right, he broke three needles. So he told us it has never happened to him before. Then we told him, welcome to the tropics. Yeah, but we couldn't let him continue breaking his needles, right? Or else he won't be able to teach us anything. So anyway, yeah, but he was nice enough. After that, he went back and did a S version, PD with the S version. He calls it the Singapore version. But yeah, it's a version with a lot of lower gears so that he can drill through our wood. Yeah, so the needle is although the needle is very small, right, the shaft length is very long. Okay, it's 40 mm, 400 mm, means that when it's drilling into wood, because it's such close proximity, right, you have something called shaft resistance. I'll let you see that later. So yeah, literally, you see this? The needle goes in, pushes the wood aside. Okay, when it exits, right, you pull back the wood and then clog the hole it created. Then as you also see that the shaft as it goes in, right, this whole area is surface area for friction. Okay, so a certain amount of shaft resistance will be seen in your reading. It's also very important to have your edges sharp. Anytime the needle goes blunt, right, you have to change it, or else your reading will be accurate. Okay, one needle is about $80. So in the tropics, we at best do 20 drills, 30 drills, not 100 or 150. Okay, where to drill? Okay, for trees, a bit more complicated. We'll have to decide where the decay is, between buttress roots and whatnot. But for conservation projects, what do we have? We have circular columns, right? So I don't have to go through this process so much. I'll just drill at the point, or I'll just evenly distribute out the drills. Okay, this is a profile. This is the resistance profile you get after you drill. So the needle comes in here, hits the wood, climbs. Okay, gets very hard resistance. So up to this point, you see there's abnormality in the wood. Visually, you can tell, right, that this quality of wood and this quality is different, right? But this is only seen after you section the tree. From outside, you probably won't be able to see this. Okay, so good quality wood means good density. Good density until this point where the wood is being degraded, then the wood density drops. Okay, which means your resistance will drop also. So the resistance will drop, and then this is the amount of wood that is not usable or in decay. Okay, you'll also notice, right, it doesn't need to be empty before the resistance drops to almost zero. Okay, visually you may see that there's still some wood material, but the quality of the wood is so bad that it's offering no resistance, means it's offering no structural support. Okay. Okay, in the resistograph, there's two curves, the drill curve and the feed curve. The feed curve is actually more important than the drill curve. The difference between the drill curve and the feed curve is the shaft resistance I was talking about. Okay, the feed curve, right, measures resistance at the tip of the needle. Okay, the drill curve measures the whole resistance. So if you take away the resistance of the whole needle and the tip, you get the shaft resistance only. But in terms of assessment, right, the resistance offered by the tip, right, which is the feed curve, right, is the most important. Okay, this is the profile of intact wood. So this is, again, the blue one is the feed curve, resistance at the tip of the needle. Okay, the green one is the resistance of the whole needle. Okay, you'll see that as it enters the sapwood, it climbs to the hardwood. This is the level of wood density, and there's no dips in the profile, means the wood is in uniform structure. It means no defects. This is tree and this is palm. You see the palm is very different. Palm is a monocot. So internally it's not dead material, it's actually live material. It's actually very, it's just made out of water, okay? Which is the reason why the profile is like this. If this profile is seen in a tree, right, the tree has to be cut, okay? But in palms, right, this is the profile. And it's also a reason why we cannot use the resistograph reliably on palm materials. I don't know whether you all got projects with coconuts or not, where coconuts are used as structure. But it won't, the resistograph will not be effective here. Okay, so example of how we do tree assessment. So we do a visual and we decide, from the visual assessment, there are two routes that are not, we think are an issue. So we start to drill all of them. And you notice, right, route 5, which is R5, right, it looks quite okay, right, from a layman's perspective, right? But if you do the resistograph, right, there is no resistance. Means this section of the root, right, is totally decayed. Okay. Similarly for root 4, right, it doesn't look that bad, but it's also decayed. When you have this kind of structure, right, it's called floating wood. It's a very degraded wood. It's there, offers a bit of resistance, but it's not connected to the rest of wood. This floating wood have no structural integrity also. Okay, we see this a lot in old structural columns in conservation buildings that are degraded. Okay. Remember I told you there's a relative measure of resistance. Okay, the healthy wood, right, is at 0.20. Okay, but you notice that the decayed wood is at under 10. Okay, so this material, right, is already more than 50% compromised. Okay with this? Okay, again, once there's a dip, it's this empty space. So 3 things about resistograph, right? Presence of decay, size of decay. So this, there's a decay, so presence of decay is there. Size of decay, that, this section here is decayed, so you can approximate the size of decay. And the last part is whether decay is propagating or not. Okay, when you have a sharp drop like this, this is a wall, internal wall formed by the wood itself, to prevent decay from expanding. Okay, so if there's a decay, right, and I see that there's a sharp drop right before the decay, right, this is actually a good thing. It's a lesser of 2 evils. Okay, it means that the tree is doing something to prevent the decay from propagating. But if the decay is gradual, right, if the profile is gradual, right, it tells me the decay is still propagating. So in this profile, one side of the tree has successfully blocked the decay. The other side of the tree, right, as it goes in, right, this decay, the tree hasn't managed to stop it. Okay, so this is not good. But in conservation projects, right, because there's dead material, right, you won't get natural blockage one. In conservation projects, right, when I see this dip here, right, it's a crack or a slot or something that was manually done for a joint. Okay. So after the assessment, right, after you compile all these data, right, you can sort of like do a rough sketch of where the decay happened. Okay, next case. This is a large tembusu tree in one of my client's house. We've been looking at this tree for 6 years, but it's only last year that when we went, and then the wood material here actually broke off. It's just a little small crack here that broke off, and then when we went around, right, we found another area of discoloration, then we decided to drill. When we started to drill the tree, this is the size of the decay within. So it's largely empty inside. It's only supported by the roots. And this size of decay, right, doesn't happen overnight. Okay, it probably took 20, 30 years to develop. The point was that we were on the job for the last 6 years. Okay, and we only, if the external signs don't tell you, you won't do the resistograph drill. It's only on the 6th year, right, where there was a sign appeared, right, then you do the drill, and then you realize actually how lucky you were, okay, to have spotted this. So visual indicators, right, there is a debate now ongoing to say that if this is a tambus tree, this size is about 2.8 meters in girth. Its growth rate is very small, so 2.8 meters in girth means that it's about 100 odd years old. So this guy has seen through 2 world wars, okay, and we are losing a lot of these trees, which is quite sad. Okay, so we went through Picus Ultras, the resistograph, which is the needle drilling micro drill. Okay, the next one is the more sophisticated Picus ultrasound, which uses sound, okay, to detect decay within wood. So sound, right, it requires material. The denser the material, the faster it goes, right. If the material is less dense, right, the sound will take longer to travel from one point to the other. But if it's very dense material, right, then it takes faster. So it takes advantage of that to decide whether there's decay or not. Okay, so largely what happens is that you put multiple sensors around the trunk, and then you start to ping. If you put 8 sensors, you start to ping one, use the hammer to knock, and then the sound will just transmit to the other receptors, and then you go around knocking all the receptors. So I think it hung. Wait, okay. So what happens is that all these sensors, right, then you have you actually you have to nail it on the tree. So this is, I think, still not considered invasive, but I find it more invasive than a resistograph. I mean, you've got all the receptors up, and then you ping one side of it, and then the noise will travel around and then form a lattice of information. Then you go down to the next guy, and then you ping the guy again. So you repeat this throughout the circumference of the tree. Okay. So once this is done, right, this is the image that you'll form. Okay. The dark brown areas are very hard wood. Okay, and means that there's no degradation. The blue one is empty. It's a true cavity. But the purple and the green colors are infected wood in process of degradation. Okay, so key to this, right, is shape formation, because you need to measure the sound of the wood, the speed of the sound. Okay, and the speed of sound depends on the distance it has to travel. So if you have an odd shaped tree, right, you really have to form the shape before the data is accurate, and that takes a lot of time, more time than the actual pinging itself. Okay, in tropical trees, right, where you have buttresses, that makes it a very complicated affair. Okay, but in conservation projects, right, again you have a circular column. Okay, and we use this in areas where the column is important. Then and it's very hard to replace the column. Then you can use the Picus ultrasound. Okay, so similarly, in this one, you don't have a central core decay, a central column decay. What you have is an open door decay, something happened here, and the decay went in. Okay, so the pikers will be able to do this for you, and it's again, it's a more sexy equipment because the details are very clear. Okay, imagine a buttress root tree. If you don't get the buttresses all right, you don't get the shape and the form all right, your data within will not be accurate. Okay. From this picture, right, this tells us largely the internal core of the tree, right, is gone. Only the buttress roots are holding up. Okay. Just a few years ago, right, this is acceptable to retain because at that point in time, the science believes that the roots alone can hold up the tree. Okay, but recently, right, this is no longer the case because if you have material here, crack propagation will form. And currently, if you have this, right, you're supposed to fail the tree. Okay, you look at the base of tree, it looks quite bad, which is the reason why I went for a piker's ultrasound, but piker's ultrasound shows that wood integrity is largely good. Okay, so you can keep this tree. Depending on the size of the tree, right, you can run up to 24 sensors, and the cables you have to manage is quite messy. Again, the pikers is only used for trees of very good, very high value, because it takes more time, and cost-wise, it's about minimum three times what you cost to do a resistograph. Even if you have done your pikers right, in terms of operating procedures, right, you will still double check the data, right, the pikers data with a resistograph drill. So at the end of the day, right, I think in terms of time, cost, and efficiency, right, the resistograph still provides the best fit for most situations. Okay, decay detection in conservation works. This is 150 Todok IA Temple. Okay, this wood, right, you can see, I don't know whether it's clear. You can see when they section the wood surface, right, it looks like concrete. I hate to see this in temples because this means that the wood is ironwood. Eucederon. This is the Borneo ironwood. This is very, very hard. I told you my needles, right? Last 20 to 30 drills, right? Okay, this if I hit this, it's about 8, and I got to change needles already. Okay, if I'm lucky, it's 8. And when you drill in, right, because the wood density is so hard, right, it will smoke. Whole needle will smoke. Okay, because the equipment is small enough, so it's very in areas where tight constraints, right, we can deploy this. Okay, this is what 200 years old, right? Yeah, so this is on the top of the roof, you know. So this was exposed to weather elements, you know. And after 200 years or close to 200 years, you see the wood is still very good quality. So ironwood is one of the best. In Mulu National Park in Sarawak, right, as a kid, I went to the national park. I went to a cave, and then there's a hole in the cave, and the ironwood has dropped down onto the floor of the cave. And then because there's a hole on top, right, the ironwood, the dead wood is highlighted by the light. 20 years later, I went back to the same cave, right, to the same spot. The tree is exactly the same. It didn't change at all. So ironwood is one of the toughest wood around. They use it for old construction, but I don't think they use it anymore. Export of the wood is also banned. Okay, this was one of the columns, but this wasn't ironwood, this was chengao. You can see that there was a central column decay. This was the other one we worked with Dr. Yu, the SUTD one, right? The 大同杜泽 and the 戏台 and the double pavilion. The wood here, it's temperate wood, so it's 樟木, right? Zangmu is camphor wood, right? So camphor wood is apparently very weak. I don't know why. So I could barely pick up resistance. See, if you see there's degradation, right? You borer attacks, like these small dots, right? There's borer attacks. So you, in this location, once you identify it visually already, right, you start to drill. And when you drill, right, you'll find there will be decay. Okay? But some of these, right, it's only out superficial discoloration. When you drill inside, it's largely okay. These are the structural support. So structural column or wood that are used for structural support, I will expect a higher density. Okay, or at least I'll prefer a higher density. These two are the same material apparently, but you can see this is higher density and there's no defects, right? This doesn't have dips that tells me there's a cavity, but the wood density is way lower than this one. Okay. So to me there's some compromise in the quality of the wood. Oh, recently we're doing St. Andrew's Cathedral for the window frames. So this is in situ. So you have to go on a crane to start drilling. For these situations, right, we usually aim for areas that we think will have highest dampness. Because the water will come in, right, at a lower point, and then because it's painted, I can't see the discoloration. So we will choose areas like this to sample. Okay. Okay, wood density wise, Eucederon. It's the ironwood acacia. This was taken, there's only one reading for auricularis that was taken in Australia, 0.68. So for us empirically, right, anything that's above 0.65, right, we say it's hardwood. And we think it's okay for outdoor furniture with little treatment. Because if you have very high density, right, wood density, right, whatever treatment you do, right, will not permeate deep. Okay? Anything that's 0.35 and below, we consider them very soft wood. This is a tembusu, a piece of tembusu left out for 6 years without treatment. Okay? It still looks okay. There's no degradation at all. Okay? This is kaya. Kaya is African in origin. We left it out for 5 years before I passed it to a landscape architect friend, and then all he did was to oil it. So you can see, right, from grey, this is exposed weathered wood, then to when you oil it and you sand it down, right, the quality of wood comes out. Okay. So in summary, what happens usually is that we will do a visual tree assessment to look out for wood discoloration, fungal fruiting bodies, termite infestation, and open cavities. Then if we think there's a decay, we'll do second level. It's either with a resistograph or a picus. Okay. And if there's no signs of degradation, right, and if it's a conservation project, right, we'll still take a reference drill for the future. So that in the future, if that beam needs to be reassessed again, right, you have a reference drill. Okay. Then the recommendations we are making, right, we usually don't make it independently unless it's really, really bad. But we will make it in consultation with the conservation specialist and the professional engineer. Okay. Any questions? So, thank you.
Okay, thank you, Derek, for the very insightful talk. I think a lot of us here who are in the conservation field would need to learn a lot from Derek. Because Derek needs to leave at about 3, so I thought I'll just open up for maybe a couple of any urgent questions or burning questions that Maybe somebody needs to clarify certain points in Derek's presentation before we move on to the discussion later. Anyone? Nope. Going. Yeah.
In Singapore, right, if it's in Orchard Road, it presents a safety issue, right, I will recommend removal. Okay, I'll give you the very famous case in Botanic Gardens, the one that came down and killed a visitor. The tree is 200 odd years old. Even if they found a defect within, right, if they found a defect within, and then that was a high use area, they would have to ask for removal.
But have you considered, like in Japan, because of special spiritual things, they build structures?
God. Yeah, we currently have a similar tree. 177 Toa Payoh is the fig tree that stopped development of Toa Payoh. It was very odd. This is about 30, 40 years ago when Toa Payoh estate was being built. So any bulldozer that came near to the tree stopped working. Any chainsaw didn't work. So they decided to not build around the tree. That tree has since degraded totally into... My first instinct when I was there was to ask the temple to cut the tree, because around it's all high target. It's those shopping mall alleys. So, yeah, but because of historical reasons, right, and religious reasons, they wanted to keep it. So it goes back to my comfort level, my understanding of the tree. So it's called tree vocabulary. So you need to understand the individual you're dealing with, whether it's what's regenerative property in this case, whether its vigor will eventually come up, whether, fig trees are different from other trees. You can cut everything, right, and it still regenerate. You can totally reduce the thing and it still regenerate. So for this tree, right, the challenge is that its regeneration is faster than the degradation. You have to get that balance towards regeneration. There's a one-day lecture by itself. So, yeah. So, and then the last thing is my comfort level. Whether I have sufficient risk appetite to manage this tree. At this point of time, there is. Okay, and we assess the tree every year or every 6 months. At which point, if conditions change, safety is not regenerating faster than it's degrading, it will change my risk appetite. And my decision to retain the tree will be influenced by this. Okay. For dead stuff, right, in conservation context, right, considerations are different, okay, because the tree is not live anymore. So regenerative properties are not my priority concern. So it becomes a structural issue, which we will always work with the structural engineer and conservation expert to decide. So like dead material, you can carve out a section, right, and then you can replace with other material. Okay, but I wanted to tell you all the failure criteria. Our failure criteria for trees, right, live trees, right, is 70% hollow. That means the tree can be 70% hollow, and I will still be able to retain it. And if the tree is 65% hollow and it failed, right, I'm still not liable, because the science tells us 70% is okay. So it goes back to whether that defect will result in the keyword is predictable failure. Okay, 65% is still not considered predictable failure. But when it's conservation context, right, it's structural already. What your structural engineer's comfort level is what? 30%. Correct or not? Anything that's compromised 30%, he takes the lead. I will not, because he's the one with the chop, you see, the tau kwa yin. He will stamp and sign his life away one. So I will listen to him. I will give him suggestions, but largely if he wants to replace the whole thing, I will. Okay?
Okay, we'll take more questions later. So we'll just move on to our next speaker, Mr. Liu Tsai. Now, it gives me great honor to introduce Leo, who is an oil painting restorer currently based in Taiwan. So I've adapted a short biography here from some information gathered from the Gallery Sun website, which features Leo as part of their restoration conservation services. I hope you don't mind. Leo received his restoration and conservation training at the Institute of Art and Restoration of the Palazzo Spinelli in Florence. And he has previously worked with the New Orleans Conservation Guild in the US, as well as Uffizi Gallery in Italy, where he had the privilege to get up close to and restore artworks by renowned artists such as Giotto and Strozzi. In 2009, Leo joined the Maastricht-based SRAL to work on the National Art Collections of the Netherlands. And following that, in 2010, he was appointed by the Dupont Museum of Contemporary Art in Tilburg, Netherlands, to restore the art installations commissioned for the Dutch Pavilion at the Shanghai World Expo. And Leo returned to Taiwan in 2012 to continue his practice and has worked on various projects since. So his presentation today will give us a glimpse of his work. So let's put our hands together for Mr. Liu Tai, who will be speaking on From Door Gods to Temples, Changing Conservation Strategies. Leo, please.